Today we are looking at topic 312, equivalent representations of trig functions, day one. We have looked and worked in different sections and learned how to write equivalent representations of trig function expressions. And we've used some identities, but we're in this lesson, we're going to really look at several more tools and more identities that we can use that will not only help us write the expression in a different form using these identities, they will also help us be able to solve a little more evolved trig equations. So today's lesson, we're going to focus a lot on kind of deriving the identities, so where they come from, and also how to just use them and practice working with them. We will move into our day two with more solving equations using these identities. So it's real important today to make sure you're doing your practice so you're getting comfortable using these identities. The identities that you see in the box here in this area will need to be committed to memory. So the best way to do that is to do enough problems that you learn them, and then you're not having to just sit down and memorize them. So I put them all together here. We've got them all in a group, and then we'll kind of go through the examples and use different ones out of this group. So the first set are reciprocal and quotient trig identities, which you already know. We know that sine is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cotan, cotan is 1 over tan, and also because 1 over tan is a reciprocal for cotan, when we use this tangent form that's sine over cosine, we can use a reciprocal form for cotan as well, which is cosine over sine. Then cosecant is a reciprocal of 1 over sine, and secant is 1 over. Set of identities we're going to look at is Pythagorean identity and the equivalent form. So we think of the Pythagorean identities as having three different ones. This is the main one, and then we can derive and rewrite it to get a Pythagorean identity with tangent and a Pythagorean identity with cotangent. We also have inverse trig identities, and so we're kind of introducing you to those today. So we have cosine negative 1 of x equals sine to the negative 1 of the square root of 1 minus x squared. You will see more references to things like this in calculus next year if you decide to take calculus. We have sum and difference identities here. So you can see inside here, it's two angles that are added or subtracted, which is where the reference of sum and difference comes from. So those you have to pay attention to. And if you notice over here, this looks a little weird. You probably haven't seen that before. But if you take this is actually two different identities. If I take cosine alpha plus beta, since plus is the top sign here, I use the minus, which is the top sign here. So it's just a way to write four identities in the path of two. And then the last set is the double angle identities. And so when we're looking at those, you see that we have a double angle for sine and we have a double angle for cosine, but notice the double angle for cosine has three different representations. And so we'll talk about that. So we're going to kind of start first, not necessarily, but by deriving, but just thinking about what does this word say, this direction say. In example one, it says, let f of x equal sine of x times secant squared of x over cosecant squared x, or I'm sorry, cosecant x. We're going to rewrite f of x as an expression involving tangent and no other trig identities. So you can see right here, we have sine, we have cosecant, we have secant, and there isn't a tangent to be had, but we're going to use our identities to help us get there. So I'm going to start with writing the problem down here, just so I have it in my workspace. Because as you all know by now, after being with me through this year, I'm a very visual person. All right, so this is what I am trying to do. And I'm trying to get and only use tangent. So there's a couple of things as we're looking at identities. The most common ones we typically use are the reciprocals. In order to use the Pythagorean identity, we have to have squares involved. In order to use the cosine double angles, there should be squares involved. So you have to pay attention to some of those basic things when you're looking at a problem, because we could have this problem where we might be able to get to our answer in a couple of different ways. So you have to remember that you have to be able to legitimately apply the rule. All right, so on this one, I'm going to start with keeping my sine x, and then I'm going to use the reciprocal for secant squared x. So what this means is secant times secant. So that means if I take the reciprocal of secant, I get 1 over cosine, and the reciprocal of the second secant will give me another 1 over cosine. So if I multiply cosine together by cosine, I get cosine squared. So I'm going to rewrite that as 1 over cosine squared. Okay? And then I'm not going to do anything with the bottom. I'm going to kind of do these out in, since we're doing our notes here, in more separated steps so you can kind of see the process. If you want to get good at this, then you've got to practice it. That's how you get good at it. So you get to where you can look at a problem and go, hey, I'm going to use a reciprocal. Okay? You don't get that way if you don't practice. All right, so now I'm going to look at the bottom, and I see right here I have a cosecant. And so I know that if I'm looking up here, cosecant is the same thing as 1 over sine. So now I'm going to take and I'm going to have sine over cosine on top, right? Because if this is the same thing as a whole number, then a whole number times a fraction is just the whole number times what's on top of the fraction, and cosine squared on bottom. And then on bottom, we have the reciprocal, which is 1 over sine x. So again, I just replaced this with its identity. So now I'm going to go up here, and I'm going to clean this up. This kind of is a gross form. It's fraction within a fraction. It's complex fraction. But remember, that just means sine of x over cosine squared x divided by 1 over sine x. And you may be more comfortable with that form, and that's okay. So when I divide by a fraction, I multiply by its reciprocal. So I have sine x over cosine squared x times sine x over 1. And when we have multiplication of fractions and we multiply the tops, and we multiply the bottoms. So the top is sine x times sine x, which is sine squared x, and the bottom is cosine squared x times 1, or cosine squared. So this should look somewhat familiar. It's an identity from that first section again. It's actually a version of the tangent identity, because tangent is sine over cosine. So I have 2 sines on top and 2 cosines on bottom. So this is just going to end up equaling tan squared x. And so that's how I can use my identities to work through a problem, be able to change identities out, and be able to simplify further until I can get it down to its most simplest form. And in this case, that was from the directions, an expression involving only tangent and no other trig equations or trig functions. So that's my third read. Did I answer the question? Yep, tan squared x. All right, example 2. So we have g of x equals cosecant x times tan x. And it asks us to rewrite g of x. So we write this expression involving secant x and no other trig values. So when I'm finished, I need to have a secant x. All right, so let's look at what we can do here. We can look at reciprocal identities. What's the reciprocal of cosecant of x? Cosecant of x. That's 1 over sine. What do we know about tangent? Tangent can be written as sine over cosine. So what do they have in common? They have sine. So I'm going to rewrite this using this first one as reciprocal as 1 over sine x times, and then I'm going to use tangent to be sine x over cosine x. So if I think about simplification, anything in the bottom can simplify with something in the top when it's multiplication. So anything divided by itself in this case would be 1. So I am left with 1 times 1 on top and 1 times cosine x on bottom. And what is another way we can write 1 over cosine? We can write that as secant. So I rewrote this in terms of secant. So did I answer my question on my third read? Did I take the g of x function and write it so that I'm only using secant x and no other trig functions? And that is the case. So I have simplified this expression. So if we had values here, we could maybe even, now that it's simplified, use what we know about the unit circle and be able to evaluate. All right, let's move on to the next page. Okay, so additionally, we're going to discover using some of these properties and being able to derive them. So the first one we're going to start with the unit circle that has point x and y. So this is the point right here, x and y. And we know from previous studies that that means that's the same thing as cosine theta, sine theta, where x equals cosine theta and y equals sine theta. So if this is cosine theta and this is sine theta, that makes a right triangle. And if it's a right triangle, then we can use the Pythagorean theorem to create the Pythagorean identity. Because all we would have to do then is we would take this leg squared plus this leg squared, and it has to equal that squared. So the cosine squared plus the sine squared equals 1. And that's our first identity. Typically, you'll see it in standard written as sine squared theta plus cosine squared theta equals 1. And that's okay because these properties are commutative. So we have our first identity that's a result of using the Pythagorean theorem. So we call it the Pythagorean identity. In order to use the Pythagorean identity, remember that they have to be squares. So I can't say cosine plus sine equals 1 or cosine cubed plus sine cubed equals 1. It's actually cosine squared theta plus sine squared theta. So if you're literally looking at the identity, that's what it's going to look like. Now, there are actually 3 Pythagorean identities. If you look at your box here, remember we said there were going to be 3, so we just found out how to get that one. Now we're going to look at these 2. Notice one of them has tangent in it and one has cotangent. And what do we know about tangent? Then we can say tangent is sine over cosine, and we know that cotan is cosine over sine. So if we keep that in mind as we're deriving these other 2, it becomes a very easy process. So in order to derive this one, I started out with the basic function. So sine squared theta plus cosine squared theta equals 1. And so I wanted the Pythagorean identity that has tangent in it. So I know that tangent is cosine over sine. I'm sorry, sine over cosine. So I'm going to divide everything by cosine. And I'm going to do it by squares because we're talking about the Pythagorean identity, and that uses powers of 2. So then we're going to simplify each fraction here. So sine squared over cosine squared. So that's going to give me tan squared theta. And then cosine over itself is just going to give me a 1. And then 1 over cosine squared is going to give me secant squared. So super easy to derive that. We started with this one and derived it through using our quotient identity. So we could also do the cotangent one by once again starting with the basic Pythagorean identity. But this time, since I want to have cotangent in my Pythagorean identity, and I know that cotangent is cosine over sine, then I'm going to take everything here, and this time I'm going to divide it by sine. So then sine squared over sine squared is 1 plus, I have cosine over sine, I now have cotangent. And then 1 over sine is a reciprocal for cosecant. So that's how we can get the 3 Pythagorean identities. This one used absolutely the most. So as long as you know this one, now you know you should be able to derive either one of these two. And that would cover all 3 of our Pythagorean identities right here. All right, looking good, guys. Okay, so another circle. This time we're going to find another identity by using the unit circle when we inscribe a right triangle on the inside of the unit circle, kind of like we did in the last example. And we can express the height of the triangle by using the Pythagorean theorem. So remember, this would be my height. So I'm going to say this is the height. And so I'm going to take, using my Pythagorean theorem, and I'm going to kind of just set it up, right? So I should have x squared plus h squared equals 1. And so now that I've done this leg squared plus this leg squared equals hypotenuse squared, I just put a 1. If you want to go ahead and put that squared there so that you'll keep track of that, that's fine as well. But what I would like to do now is solve for the height. I want to find a sort of measurement for this. So to get the height by itself, I'm going to say h squared equals, and I'm going to have the 1 from this side, and I'm going to subtract x squared. And then how do I get h by itself? And then I would normally take plus or minus, but because we're talking about a distance right here, we only have to worry about the 1 minus x squared. So now I know that the height right here is the square root of 1 minus x squared. Okay, so as we're looking at where we're at now, we want to go back and review a few things. We know that cosine of theta is x over r, and sine of theta is y over r. We learned that in our first lesson. It's the ratio of that horizontal displacement to the radius and the vertical displacement to the radius. So keeping that in mind, now let's turn these ratios into something that will go with our triangle here. So what I mean by that is if I want in my triangle right here to figure out what cosine of theta is, then I can say that's x for the horizontal displacement here over the radius. And then I can say sine of theta. So remember, sine of theta is going to be the y, and we just found the y to be the square root of 1 minus x squared over the radius, which is 1. So now, how do we get from here to one of the identities in our table? So notice that they have x's in common, but this one has an x under the radical. They do have thetas in common. So if I can solve each one for theta, then I can use my substitution property and set them equal to each other. So if I want to get the theta out from inside the cosine, I'm going to do cosine to the -1 of x equals theta. And then over here, I'm going to do the same thing. I'm going to say sine -1 of the radical 1 minus x squared equals theta. And once I have these two things set equal to theta, then these two things can be set equal to each other as well. So cosine -1 of x equals sine -1 of the square root of 1 minus x squared. So that gives me my identity, and these are actually the inverse identity. And again, we don't use them as much as. All right, so this is kind of going through the process. Does explain the process in here as well, so you can refer back to that. So let's move on to our next problem, which is going to be practicing simplifying again, and then we will look at the next group of identities, the sum and difference, and the double angle. So as we look at example 3, the function f is given by f of x equals tan x over cosecant x. We want to rewrite f of x as a fraction involving powers of cosine x and no other trig functions. So powers of cosine x could be cosine squared x, cosine to the power of 3x, or just cosine x, because technically that is a power, it's just the power of 1. All right, so let me write down my problem over here so I can have my visual when I'm working. So there's a couple of ways that you can handle a problem like this. Sometimes you can think about pulling the numerator off because we know when we multiply fractions, we multiply the tops and we multiply the bottoms. So this could be the same thing as tan x times 1 over cosecant x, and then you might be able to proceed from there. But I'm not going to do that. I'm going to use my reciprocal and my quotient identities. And I do want you to be careful here because not everything should you go directly to the fractional identities, because you could be making a problem more complicated for yourself. But in this case, I can see some connections, right? I know that sine can be sine over cosine, and what's the reciprocal for cosecant? 1 over sine. So you can see again, I have a way to connect these two things together because they both have a sine x as part of the identity. So I am going to start by taking tan x, which is going to be sine x, over cosine x. And I'm dividing that by the reciprocal of cosecant x, which is 1 over sine x. And so again, like we said last time, if you don't particularly like it written like that, this is the same thing as sine x over cosine x divided by 1 over sine x. And so what do we do when we divide two fractions? We can multiply by the reciprocal. So we have sine x over cosine x times sine x over 1. So once we get to this point, then what would be the next step? So I'm going to bring it up here. I'm going to multiply the tops and multiply the bottoms. So sine x times sine x is sine squared x over cosine x times 1, which is cosine x. Now, remember how it said powers of cosine? Well, right now, I don't have any powers of cosine. I have powers of sine. So what I'm looking for here is a identity that deals with powers of 2. So if you go back to your first page, we could be looking at Pythagorean identities, or we could be looking at double angle identities. And so I'm going to go with the Pythagorean identity. The Pythagorean identity, if I have sine squared theta, then it's going to equal 1 minus cosine squared theta. So I can rewrite these to get sine by itself or cosine by itself or tangent by itself, secant by itself by just manipulating that around. Okay? So let's do that. So I'm going to replace sine squared x with 1 minus cosine squared x. Notice that this is a process of replacing. When I see an identity I want to use, I'm going to take out what's there and replace it with an identity. And so now I'm over cosine of x. So have I accomplished my task? What was my task? To write it only in powers of cosine, and I did. This is a square right there, a little smushy, but it's a square. That's a power of cosine, and that's a power of cosine. So that's my final answer. And as we've been practicing all year, your answer should be easy to find because it should be the last thing in your work. And you shouldn't have to box it or anything like that if you've been doing your work correctly. All right, so that's another practice rewriting, but a little differently. We use the identities a little differently this time. All right, so two additional identities that are important are sum identities for sine and cosine. And given any two angles, alpha and beta, we can have this identity. So we can have sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta, or we can have a cosine identity. So using these two identities, we can also derive what they are for minus and what they are for double angles. So double angles, we're looking at these right here. And then sum and difference are these right here, okay? So when we're using sum and difference, we're paying attention to what is the trig function on the outside. Is it sine or is it cosine? And then what's happening in here? Is it addition or subtraction? And that's how you decide which to use. The double angle identities are actually can be derived from using some of the things and techniques we've already talked about. So at this point, we have one of our identities here. We have one of our identities here. We also have minuses that we can look at. And you can find all of those on your first page right here. So if you're going to have sign on the outside and a plus in the middle, then you're going to use the top sign over here and it's a plus. There's a minus in the middle, which is the bottom sign here. Then you're going to pick the bottom sign over here, which would also be a minus. So we'll have to worry about, we will worry and use those. But let's start with how the double angles are tied to that. So these steps 1, 2, 3, 4 here are about taking a double angle and turning it into something like 4 theta instead of just 2 theta. So we're going to come back to that and we'll do this on this side. Over here, I want to look at the identities for sum and difference. So I'm going to let theta equal alpha and beta. And so what that basically means is that my alpha and my beta angles are going to be the same. So going to use this one right here, I'm going to have sine of theta plus sine, not sine, excuse me, inside plus theta. So I've got this situation here where A and B are the same, so both of mine are going to be theta. Then if I were to actually put it in here, I'm going to have sine of alpha cosine of, theta plus cosine of theta sine of theta. And all I'm doing is following my rule expansion on this side right now. So then when I look at this, I can see that sine of theta cosine of theta is the same thing as cosine theta sine theta because we know that multiplication is commutative. And so basically what we have here then is sine of 2 theta equals, and so I have one of these right here and I have one of them right here. So altogether I have 2 sine theta cosine theta. And so we just derived one of the double angle identities, and that's the sine one right here. So we use this to get this. All right, so that is that one. Let's do the same thing over here for cosine alpha plus beta. So we would have cosine, and then I'm going to have 2 of the same angle. So then when I put it in the expansion of this identity on this side, then I'm going to have cosine theta sine theta minus sine theta sine theta. Let's see, cosine, cosine, not sine, excuse me. So then as I'm looking at this, I can see that I have cosine 2 theta equal, and a cosine times a cosine is cosine squared theta minus, and then over here a sine theta times sine theta is sine squared theta. So I found one of my double cosines, which is this one right here. Then we can use what we know about this to derive the other two, much like we did Pythagorean identities. Okay, so if I'm going to derive the Pythagorean, so here's one, I'm trying to do it in color so you can kind of see the differentiation between the two problems. So we're going to start with cosine of 2 theta and develop the other two. So now I'm going to use this version of cosine 2 theta and the Pythagorean identity the main one that says sine squared theta plus cosine squared theta equals 1. All right, so I'm going to have cosine 2 theta. And I'm going to do cosine 2 theta minus, and then I'm going to use the Pythagorean theorem to turn sine squared theta into cosine. So I can do 1 minus cosine squared theta. And so then what I have is a place where I can collect like terms. And so I have cosine 2 theta equals, so that's a -1 and a negative is a positive cosine. So when I collect my like term, these two things can collect together and be 2 cosine squared theta. And then when that's distributed through, that's just -1. So you can see we used the first cosine 2 theta and the Pythagorean identity right here to create another version of that angle. Okay, and so if I'm dealing with a problem that has cosine and sine and I need double angles, I'm probably going to use the top one. If I am working with a problem that's only in terms of cosine, then I'm going to use this one. And we can follow that same procedure through to do the last one right here. So I can say cosine of 2 theta equals, and so what I'm doing now is I'm using the sine version of cosine. So instead of cosine squared theta, I'm going to put 1 minus sine squared theta, my Pythagorean identity. But this time I'm going to have minus sine squared theta because that's this part of the identity. So this time we replace the sine. This time we're replacing the cosine. And so now I'm going to have cosine of 2 theta equals 1, and I have 2 negative sine squared, so it's going to be -2 sine squared theta. So that's how you could derive that third one. So we've looked at an example of the sum angles. We've looked at how to derive the multiple angles using the sum or the difference there. So the only other thing that I really want to talk about in this section is that sometimes we don't just have cosine of 2 theta, we have something like this. So we can break that down to get sine of 4 theta by using what we know about the rules, okay? So remember the double angle for sine is sine of 2 theta equals 2 sine theta cosine theta. So you can look that up on the front page if you've forgotten. But that is in the double angle box on this side. So there's only one angle for double sine, but there are one identity for double sines, but there could be 3 for cosine, depending on what you're trying to accomplish. All right, so here is my identity. Well, this problem right here says that we're trying to break it down into sine of 4 theta. So what I'm going to do is I'm going to take sine of 4 theta, and I'm going to break that up. I'm going to say sine, and on the inside, I'm going to take 2 theta times what gives me 4, and that's going to give me a 2. So why am I doing that? Because this rule is in terms of 2 theta. So I want to be able to convert this using that fact of 2 theta. So what we're going to do right now is we're going to let u equal 2 theta. So this piece right here is going to be my u. And so when I rewrite this then, I'm going to have sine, and over here, we broke this up into 2 theta times 2. So this is going to be my u times 2. All right, are we okay so far? And then we're going to have on the other side 2 sine u cosine u. So remember, these are in terms of the same thing right here and here. So that's why I'm doing that. And so now I'm going to put back in my u. So I just took the 2 theta out to help me be able to see what this is going to look like simplified. So if I put my u back in here, that's 2 times theta, or sine of 4 theta. And then I'm going to have 2 sine, and once again, my u was 2 theta, and then cosine, and my u once again is 2 theta. Oops. So now we have a way to take something in terms of 2u and use your double angle identities, but we can expand that out to be like sine of 4 theta, sine of 6 theta, things like that. Okay? So that's an example of how you can adjust, and that's what these 3 steps here are, is showing you how to go about what we just talked about right there. Okay, so let's do another practice example. We've been talking about proving some identities here for a bit, so let's go back. Which of the following is equivalent to the expression 2 sine pi over 14 cosine of pi over 14? So the first thing that we would want to kind of think in our mind is, what identity might this look like, right? So if I have 2 sine something, cosine something, and the somethings are the same, which happen to be here, then we're talking about a version of this identity, right? 2 something with the same theta as cosine something. All right. So I'm going to start by identifying these 2 things. So I'm going to say my A is going to be pi over 14, and my B is going to be pi over 14. So I'm just assigning this to be my A and this to be my B. All right, so now we're going to kind of work backwards and see what we can figure out to be true. So I know that if I use that double angle identity that we talked about, I could say sine of 2 theta equals 2 sine theta cosine theta. So that's the identity that I'm going to use. So keeping that in mind, now we do know that both of these angles are the same thing, right? So I can look at what that might look like. So if I look at this piece right here, I'm going to say sine of 2 times, and what in this problem would be my theta? My A and my B are the same angle, so my theta is pi over 14. So as I simplify pi over 14, that equals pi over 7. So what that tells me then is sine of 2 theta has to be equal to the sine of pi over 7. So when I'm looking at my answer here, I use my identity to figure out this side. And I can see that I have that answer right there, which is C. All right, so now let's see if you've absorbed some of the stuff that we've been talking about. Example 5 says the function k is given by k of x equal to 4 cosine 2x. Which of the following is an equivalent form of k of x? So I want you to use your identity, and I want you to work through each of these 4 choices and show me what you get when you work through each of those 4 choices. And then we can decide what actually is the equivalent trig function to 4 cosine 2x. So go ahead and pause your video and start working through the problem. As always, I'm going to keep track of my problem right here. And so I'm going to work through each one of these, right? So this one, this one, this one, and this one. Pause your video. Okay, so as you thought about that, I'm looking at this and I can see that I have a double angle here times 4. And so there are 3 options for double angle. So I'm going to do cosine 2 theta minus sine squared theta. I'm going to look at 1 minus 2 sine squared theta. And I'm going to look at 2 cosine squared theta minus 1. And so using what you know about double angles, I want you to work through these 3 statements and figure out which of these up here is going to be equivalent. And maybe you can just look at it and see that's one thing, but we are practicing the process and practicing using the equations. So I want you to do the steps below each choice. Pause your video. Okay, so as you work through, so remember the three identities are cosine squared theta, sine squared theta. And here we're doing 4 times whatever that identity is. So 4 times whatever the double angle is. So 4, and this is the version that I used here. So when I distribute my 4 through, I get 4 cosine squared theta minus 4 sine squared theta. So that doesn't appear to be any of our choices. So let's keep moving on. So now I'm going to do 4 times this double angle, which is right here. So I distribute the 4 through and I get 4 minus 8 sine squared theta. This one is not going to work because we have cosine there, so we can rule that out. This one we could rule out from the first one because it has to be a minus inside, and here it has a plus inside. So we can get rid of that. And then when I see this one here, it's this answer choice. We have cosine minus this, and this one is just sine cosine. So that one's not going to work. And then when I put my last one in, 4 times the double angle identity of 2 cosine squared theta minus 1, then I distribute through and I get 8 cosine squared theta, and then 4 times 1 gives me 4, which is in fact choice C. Okay, so example 6, that should look familiar. It should look like your sum and difference identities. So as we're figuring out how to put these together, I'm always looking for cosine, cosine, sine, sine, or are they different? So if it's cosine, cosine, sine, sine, then when I look at my sum and difference, I want cosine, cosine, sine, sine. That's not it. So I'm over here, cosine, sine, sine, sine. So I know it's going to be cosine, and then it's either going to be alpha plus beta or alpha minus beta. And I figure out that sign by looking over here. So when I look in my problem right here, I can see it's connected by a negative. So over here, the negative is on top. So I'm going to condense this back in with a plus sign. All right. So I'm going to say my alpha is pi over 8. My beta is pi over 6. So that's these two angles. So this is going to be my alpha, my beta, my alpha, my beta. Okay. Now I'm going to put it into my statement. So we said we were going to do cosine the two angles, and it was going to be a plus between them. So now I put my angles in. So I'm going to have cosine of pi over 8 plus pi over 16. And then I need to get a common denominator, so I'm going to multiply the bottom and the top by 2. So I'm going to have cosine of 2 pi over 16 plus pi over 16. So if I have 2 of them plus 1 more of them, I have cosine of 3 pi over 16. And then if this were a unit circle value, then we would be able to take it one step further and evaluate it and say this was equal to whatever the unit circle value would be. Since this isn't a unit circle value, then this would be as far as the evaluating or rewriting it in the equivalent expression could be. So identifying your angles, figuring out which part to use based on if it's the same trig functions on both sides of the connector and what connector it is, plus or minus. All right, so let's see. We've looked at a lot of identities. I have 2 circles here. This is angle alpha, which goes from here to here. This is angle beta, which goes from here to here. So what I want you to do is to use the 2 coordinates on the circles, the proper angle, and then I want you to find cosine of 2 alpha, sine of alpha plus beta, cosine of alpha minus beta, and sine of 2 beta. So you're using all of your, using all of your identities here to answer these 4 questions. So go ahead and pause your video and work through A, B, C, and D. All right, so the first thing that I did is I went up into my triangles and I figured out what my sine and cosine were. So I have the horizontal displacement over the radius and the vertical displacement over the radius. And I went in and ahead and found that for this circle, which has point P in it, and this circle, which has point Q in it. All right, so then the first one said cosine of 2 theta. I chose to use 2 cosine squared theta minus 1. So when I plug in my values, I have 2, and then cosine is negative 5/6, and I'm going to square it according to what it tells me right there, minus 1. So I get 2 times 25 over 36 minus 1. So when I multiply these two fractions together, I get 25 over 18 minus, and I changed the whole number 1 into the fraction 18 over 18 so that I could combine my numerators. 25 minus 18 gives me 7 on top and the 18 on bottom. So that's my answer for A. For B, we're using the sum and difference formulas, and it gave me sine of theta plus B, so I just finished the rest of the identity out here, which will be sine alpha cosine beta plus cosine alpha sine beta. So then I went in and plugged in my values I found before I started. So sine of alpha is root 11 over 6 times 2/3 plus negative 5 over 6 times square root of 5 over 3. So then when I multiply the tops together, I can simplify 2/6 before I start. So I'm going to have root 11 times 1 over 3 times 3, which gives me 9 on the bottom. And over here, this is a negative, so I do have a negative there. Nothing here is going to simplify, so 5 times root 5 is just 5 root 5, and 6 times 3 is 18. So if I multiply the top and the bottom by 2, then I can combine them over my common denominator of 18, and that would be 2 times 11 on top, plus or minus. In this case, I'll let the minus override 5 root 5, and so that's what part B would look like. Part C as a difference formula. So cosine alpha minus beta. So I finished the identity here, and then I plugged in my values. So cosine of alpha is negative 5/6. Cosine of beta is 2/3. Plus, because that's the connector I was looking up, sine of alpha would be root 11 over 6, and sine of beta would be root 15 over 3. So remember, when I have radicals and I'm trying to multiply them together, I can multiply the radicand that's underneath if they're the same kind of radical, like they have to both be square roots or both be cubed roots, something like that. All right, so 11 times 15 gives me my 55. 6 times 3 is 18. 5 times 2 gives me a negative. 5 times 2 gives me a negative 10 over 6 times 3 is 18. They already have a common denominator, so it's just a matter of putting the numerators together. The negative 10 from the first fraction plus radical 55 from the second fraction, all over the common denominator of 18. All right, so this time we're using a down to part D here. So I am using my identity of sine of 2 beta. This is the way I wrote that. And that's because if you look at the problem here, it's 2 beta. Okay. So then I'm going to finish my identity here. So I'm going to have 2 sine beta cosine beta. That's the double angle for sine. And so then I put in a 2, and sine beta was root 5 over 3. Cosine beta was 2/3. Nothing here is going to simplify. So 2 times 2 is 4 times root 5 on top, and 3 times 3 is 9 on bottom. So my final answer is 4 root 5 over 9. Okay, so one more last look. Today was about you getting comfortable with all of these identities and start to get them committed to memory. We practiced simplifying using the identities in different ways. We derived most of these identities so you understand where they came from. So go ahead and do your daily practice and make sure you're practicing with these. It's the only way you get good at using identities effectively and efficiently is if you practice them. You need to do enough of these problems where you recognize the pattern when you see it. All right, thanks so much, guys. We'll be back next time for part 2, where we're going to use these identities and we're going to focus a little bit more on solving trig equations, where we can use the identities that we learned today to help us move the solving process along. See you next time. Bye.